Welcome again. We will now proceed with invited speaker 5. The title of this lecture is Advanced Mathematical Modeling Through the Lens of Modern Fractional Calculus. The session chair is Professor Dr. Özlem Defterli and our distinguished speaker is Professor Dr. Amin Jajarmi. I now hand over the floor to our secretary.
Hello, everyone. Welcome to our today's afternoon session of our conference. First of all, I also myself want to thank the organizers, especially Professor Mehmet Yavuz, for giving me the chance to introduce my dear friend, Professor Amin Jajarmi. We know each other since some time. And we have also
2016.
Yes, 2016. Since 2016, almost 10 years.
In Ankara.
We have some common work also in the field of fractional calculus, especially in the optimal control area, and some applications in mathematical biology as well. And we are both mentored by our dear professor, respected professor, Professor Dr. Dumitru Balano. You may all know he is a very important scientist in the field of fractional calculus and its applications. So I am sure that he also will be honored by today's with the presentation of Amin and myself. We are both here with his contributions also. So let me introduce very briefly my dear friend Amin, Professor Amin Jajarmi. He is currently working in University of Bojnord in Iran in the electrical engineering department as an associate professor. And his main research areas are optimal control, fractional calculus, mathematical modeling, and chaos also. He has several papers in the field, very good researcher. He has almost Ash index like 49, as far as I know. And he has several citations, very important papers with huge impact in the field. So therefore, he has a lot of citations like 7,000, 8,000 and so on. So we are lucky to have him here today. So I will give the stage to him for his valuable presentation. And the title is Advancing Mathematical Through the Lens of, I missed lens. Yes, can you? Yeah, through the lens of modern fractional calculus. So please, Professor.
Thank you, dear Özlem. Hello, everyone. Can you hear me? Hello. Okay. Hello, everyone. Thank you, dear my friend, for your nice introduction. As my friend said, my name is Amin Jajarmi. I'm working as an associate professor at the Department of Electrical Engineering at the University of Bojnord in Iran. I'm so happy to be here, this highly prestigious conference. And I would like to express my sincere thanks to my friend, Professor Mehmet Yavuz, for inviting me. As you see, the title of my presentation is Advancing Mathematical Modeling Through the Lens of Modern Fractional Calculus. The outline of my presentation is available here. First, we give a brief introduction. Then we introduce some necessary definitions and preliminaries. In the next section, we define generalized form of fractional differential equations. We discuss existence and uniqueness analysis for these equations. Also, we propose two numerical methods to solve them. As case studies, we examine the effectiveness of our proposed approach in two cases: world population growth and blood ethanol concentration. Finally, we conclude our talk with some concluding remarks. Let us start with some basic questions. We work on mathematical modeling. So the basic question is that, what is a model? Basically, a model is a set of equations that describe the relationship between system variables. The next important question is that, why do we need mathematical models? We need it to improve understanding of systems. We need models to design controllers for new systems. Also, we need models to optimize system operating conditions and many others. Let me show these features by an example. In designing a controller, what is the importance of model? In designing a controller, we must first define control objectives. Then we develop a process model. Why? Because we implement the effectiveness of the controller first on the model before implementing on the real cases. Then we test the controller on the model through some simulations. If it works well, then we can implement the controller on the real process. Therefore, the importance of the model here is that before implementing the controller on the real process, we can test it on the model, and if it works well, then implementing on the real process will start. Therefore, mathematical modeling is not only attractive, but also necessary in different fields. For example, like in control engineering, in mathematical biology, in physics, and many other fields. Besides, when we talk about mathematical modeling, we should mention the fractional calculus as a powerful tool in mathematical modeling. What is fractional calculus? Fractional calculus is a branch of mathematical analysis that generalizes the concept of integer order derivatives and integrals. In fact, in fractional calculus, instead of using integer order derivatives like first order derivative, second order derivative, we work with derivatives and integrals with fractional or non-integer orders like 0.5, 0.6, and many others that are not integer. Fractional calculus has many applications, especially in mathematical modeling. You can find the application of mathematical modeling, a fractional mathematical modeling, in biology, in mechanics, in physics, in electrical engineering, and many other sciences. Why? Why is the importance of fractional calculus in mathematical modeling? What fractional calculus brings us in modeling? Fractional derivatives and integrals inherently possess memory in their definitions. These features is very important in the modeling. According to this feature, we can have more accurate models for the systems with inherent memory, like biological systems. Due to many successful achievements in fractional calculus, especially in modeling, there has been a growing interest to generalize the traditional and conventional concepts of fractional calculus, both in theory and practice. Due to this motivation, recently, under the leadership of Professor Dumitru Balianu, we have published several papers on the generalization of fractional calculus, means using modern types of fractional derivatives and integrals, especially in modeling and control. Here you can see some of our recent publications. In first one, we studied a new intervention strategy for an HIV/AIDS transmission by a general fractional modeling, not conventional fractional calculus. This work was published in a JCRQ1 journal, which is a top 10% journal. Also, the paper became highly cited and hot paper in the Web of Science platform. The next work, a new comparative study on the general fractional model of COVID-19. Again, in a Q1 journal, top 10% one, and a highly cited paper. The next one, the application of general fractional calculus for thermodynamics, another Q1 journal and highly cited paper. The next one, as a physical application of modern fractional calculus, the application of general fractional Lagrangian approach for a capacitor microphone case study. Also in the control, using general derivative operator for optimal control problems for another biological system, and many other papers, all of them in high quality journals and mostly became high influential according to Web of Science, most of which became highly cited and high paper. What is the message of these works? The main message of these works is that a single kernel in the fractional calculus modeling cannot describe all ranges of phenomena. Indeed, when we define integral and fractional integral and derivatives, you can select a kernel, which with one kernel, we may have a better model for one process, and with other kernel, we may have a better model for another process. Therefore, this idea, flexibility in choosing the kernel, provide a degree of freedom in fractional mathematical modeling. Traditional fractional modeling had a flexibility due to fractional order. By changing the fractional order, you may have a better model for a special process. Here, beside the fractional order, we change the kernel. We choose different kernel, which provides another degree of freedom for better mathematical modeling. The most important point is that how we can select the best kernel. We have different kernel function. Which of them is the best? The answer can be provided according to the real data. For a special case, according to real experimental observation, you can select the best fractional order as well as the best kernel function. And for another phenomena or another system, you may find another kernel which has best fitting to real data. However, we are at the beginning steps, so the usefulness and efficiency of these interesting ideas should be examined with different and several practical cases. Motivated by this introduction, the main aim of this talk is to introduce new fractional mathematical models for two special cases: world population growth and blood ethanol concentration. And we will try and we will test which kernel provides better answer. We use some comparative studies using real data to verify the validity of our proposed approach. In the next section, I want to provide some definitions and preliminaries about this modern and new fractional calculus concept. Maybe some of you are familiar with this concept, but these definitions is useful for who are not familiar with basic fractional calculus definitions. Here, we describe the fractional derivatives and integrals, which is based on its kernel is based on another function. Then we review some useful properties of these operators. Let us start with definition 1. Let positive Q be fractional order. J is the time interval. Y is the integrable function, the function under fractional operator. Psi is an increasing function which will introduce our kernel function, which will build our kernel function. Psi should be an increasing function, and psi dot should be non-zero. Then we define the qth order fractional integral of y with respect to the function psi as in equation 1. Equation 1 provides the definition of psi Riemann-Liouville fractional integral. At the next definition, we introduce the psi Riemann-Liouville fractional derivative as in equation 2. As you can see, the integral, we have a kernel in the integral, which is based on the function psi. By changing the psi, you can have different kernels, which is the main concept of our approach. Next definition provides the left psi Caputo fractional derivative, as in equation 3. In particular case, in general, we consider the fractional order Q to be a real number. But in a special case, we can consider Q between 0 and 1, which provides the psi Caputo fractional derivative as in equation 4. According to these definitions, we have some properties for these operators. For example, in this lemma, we show the semigroup property for these operators, for psi Riemann-Liouville integral operators, as in equation 5. We have another property. We can compute the psi Riemann-Liouville fractional integral for a special function y as in equation 6. We defined psi Riemann-Liouville Caputo and psi Riemann-Liouville and Caputo differential operators. These two operators have connection with each other, as in equation 7. Another important property is antiderivative property. If you apply the psi Caputo fractional derivative to a function, next psi Riemann-Liouville fractional integral, you can recover the original function, which is a very important property in mathematical modeling. After these definitions, we define a fractional differential equation according to psi Caputo fractional derivative. So we have equation 9. In this equation, the function g satisfies the Lipschitz condition as in equation 10. For this new type of fractional differential equation, first we have to prove the existence and uniqueness of the solution, which is very important. Here, we, according to this theorem, we can prove that if g be a real-valued continuous function satisfying the Lipschitz condition, then there exists a unique solution, there exists a solution sequence that converges uniformly to the unique solution of the fractional initial value problem 9. By proving this theorem, we can be sure that our new form of fractional differential equation has a unique solution. Let me pass the proof. According to our time limitation. In the proof, we defined an error function and show that the error tends to 0. Next, now we defined a new a new form of fractional differential equation. In the next step, we prove the existence and uniqueness of the solution for this type of equations. And now we have to provide numerical methods to approximate the solution for this type of equations. Here we introduce two numerical methods, and which their convergence is guaranteed. In this theorem, we provide our first numerical method to solve the considered fractional differential equation. Again, if G is a real valued continuous function satisfying the Lipschitz condition, then the sequence of approximations yn provided by equation 26 according to a successive substitution procedure converge uniformly to the unique solution of the fractional initial value problem 9. Therefore, since this sequence is convergent, after a finite steps, you can have an approximate solution with enough accuracy for your considered fractional differential equation. Second numerical method, to introduce our second numerical method to solve these equations, first we convert the fractional initial value problem to an integral equation. So we have the equivalent integral equation 27, which is the same, which is equivalent to our fractional differential equation. Next, we consider a uniform mesh on J with the time step size h. We denote the time at node k by tk and consider yk as the numerical approximation of y at tk. Then we find equation 28. We approximate the integral part by equation 29 based on the product rectangle rule. And finally, we have our proposed numerical method as in equation 31, in which the coefficients can be computed from equation 32 or 33. Now we have to apply an approach on case studies to show its effectiveness. Without practical case, we just do some only mathematical manipulation. But with a good case study, our approach will be meaningful and it will justify our mathematical trial. Our first case study, we consider world population growth, which has previously been modeled by an ordinary differential equation as in equation 34. In this equation, P denotes the population at time t and lambda represent the difference between the fatality and birth rates. We introduce equation 35 as our new model by using Psi-Caputo fractional derivative. We have real data here to verify our results. These data started from the year 1990, it ended at the year 2010 and counted every 10 years. We examined various kernels or various Psi functions. For example, we consider Psi equals to 0.5 t ln t plus 1 or t plus 100 power q, t plus q power q, t and 1.5 t sine 0.1 t. In this table, you can see our comparative results based on relative error or distance from real data. For each special case of Psi function, we find the best fractional order in that case. At the beginning of my talk, I told that in fractional modeling, here in our approach, we have 2 degrees of freedom. First, the fractional order. Second, the kernel. So if you select a kernel, you have another flexibility, okay? Another flexibility to provide a better model by changing the fractional order as in traditional approaches. So in this table, you can see different kernels, and for each case, you can see the best fractional order together with its associated relative error. Here, you can see again comparative results by some figures. And as a conclusion, our numerical achievements here conclude that our fractional system for the world population growth with Q equals to 0.8594 and psi equals to 0.5 TLNT plus 1 forms the best model between other derivative orders and kernel functions. So in this domain of search, which is not very big, according to these comparisons, we find the best kernel function and best fractional order, which follows better among the others our real data. Our next case study, blood ethanol concentration in a human body. Previously, this case has been described by ordinary differential equations in previous references. In equation 36, you can see S and B, which are the alcohol concentration in a stomach and blood, respectively. We fractionalize this model to provide equation 37. We try again some kernels. We change our kernels, and according to table 3, we have a set of real data to test and verify the final conclusion. Comparative results for different kernel functions together with the best fractional order for each case are provided in table 4, and simulation results versus real data are shown in figures 4 and 5. And as a consequence of our comparison, we found the best model between the other derivative orders and kernel functions, which is obtained by the Psi-Caputo fractional system with Q equals to 0.997 and psi equals to T plus 100 power Q. Finally, let me finish my talk by some concluding remarks. This research proposed a new formulation in fractional calculus for mathematical modeling purpose, especially for 2 case studies, world population growth and blood ethanol concentration in a human body. We used the new types of fractional derivatives, fractional and integral derivatives, whose their kernel is defined based on another function. Meanwhile, we provided some comparative and numerical results to show the effectiveness of our proposed approach. As can be seen in our figures and tables, the best approximations were obtained when the problems were modeled by using the Psi-Caputo fractional derivative than the other cases of fractional operators, and even better than the integer order case. As a result, our achievements here verified the usefulness of using general fractional operators for modeling purposes in practice. Here you can see the references of my presentation. And finally, I would like to thank you very much for your attention.
Okay. Thank you to Professor Jajarmi for this nice talk, which improves, how to say, which exactly gives the importance of fractional operators in modeling area. So any questions or comments regarding the presentation? Even in the online, are there any questions in the online? Okay, so I
There is one from
Okay,
Professor.
let's take it. Professor Jafari.
Can speak now.
Thank you so much. It was very interesting. I just want to ask you about the psi-t. You defined a few functions, so I just want to know, is there any limitation for this function or no?
Hello, Professor Jafari. Nice to meet you.
Hi, how
Here,
are you?
thank you. Actually, finding the best kernel is an optimization problem, which the variable is a function. I think it can be the forward of this approach, but here we just to show that by changing the kernel, we may face an improvement. So we just select not randomly, we use these functions from previous sources, but for a better finding, I think an optimization problem in this type that a variable function should be done.
Thank you so much.
You're welcome.
Okay. I have some not questions, but just to
You can ask instead of the material as well.
Okay, just one thing about your numerical results for the applications. So you select for the given specific system or problem or real data, you justify the optimal kernel and the order of the fractional derivative, and you did the fitting very well. But what about the future predictions of the same system, means forecasting? Can you also do the forecasting to predict the future behavior of the same system?
Let me say something I told to Professor Jafari as well. We didn't find the optimal kernel. We select some 5 or 6 functions, and among them, we select the best. So you cannot claim that this is the optimal function. So, and for the prediction, we can try, but according to our real data, we
You don't have
just
the rest.
yes, but for the
But
other cases,
Yeah,
one of the main target of mathematical modeling is prediction.
yes.
So
prediction.
by training the model, we find a good model, and the usefulness of this model is prediction.
For forecasting
But in our case, no, we didn't prediction because we didn't have such a data.
Yeah,
for
but
this test.
yes, I understand. But the problem, the importance is, as you said, doing the forecasting, the predictions, because in real world, the data is limited. The experiments are limited. Doing the experiments are expensive. That's why when we do the fitting performantly, we should use our mathematical model that we constructed and which fits the real data well. We can use our model to do the predictions without any
Yes.
cost, because doing experiments usually costs a lot, and that's why we don't have real data for the long time. So I think your models and results will help this, your approach.
Yes, I agree with you. At the beginning of my presentation, I told about the importance of mathematical modeling and control. The main important point is that you can implement the controller on the freely on the model. If it works well, then you can apply on the real process. So I agree with you, but for this process, training and testing or predicting, we need much more set of real data, not with 10 or even maybe more than 1,000. You can use, for example, 70% for training
Yes.
and the other for test
Testing,
or
yes.
prediction. According to the limitation of accessing to real data, maybe it's
And also, as an expert in the field, maybe you'd like to give some suggestions or some future directions for the young researchers that we have. Just a moment, please. I will give you yes. What you can suggest about the open problems in the field of fractional calculus or mathematical modeling, and how they should work with the real world data. Any suggestions, directions, or comments for especially for young people because they are doing theses and so on? It will be helpful.
in relation to my presentation, as I told to my friend Hossein, finding the best kernel is not an easy task. Because you encounter with an optimization problem, not a static, dynamic optimization problem. The variable is a function. So working on this topic, according to my presentation, can
Is
be
an open
nice. Yes.
productive.
Yes. But and more general, I consider a special type of fractional calculus, fractional derivatives, whose kernel is defined based on another function. We have recently types of other fractional operators. So young people like
Can go, yeah,
like me
can go in this
can
direction.
consider other types of fractional calculus and do meaningful comparison to find. I think we cannot find the best fractional operators for all phenomena, but for special cases, we can consider more recent fractional operators to check which of them works better.
Thank you very much, Professor Jajarmi.
Professor,
So let's, yes, Professor.
I'm Professor Osman Taylan from Istanbul Technical University.
nice to meet you, Professor.
Nice to meet you. Welcome to Konya, to Turkey. It was a pleasure to listen to you.
Thank you.
And thanks for the contribution of Professor Defteri as well. My question is, it seems I'm not mathematician, by the way. Your case, your study is just about the time series data, right? Is it true?
Not time series, a set of
We have single variable. Like with
Single.
you have multiple variables, how are you going to deal with the problem? Because in the real life problems, we don't usually have single variables. I mean the predictors. We have multiple predictors. How the shape of your function would be, and can your function be used for the prediction of multiple predictors?
In mathematical modeling, especially fractional mathematical modeling, increasing the number of parameters and state variables will increase the complexity of computation. Not only state variables, even parameters. If we have different states or different variables with different real data, we can compute absolute error for each of them, and then consider combine these errors together, or put a weight to each of them. For example, for the first state, you have a set of real data and a numerical result. These provide a relative or absolute error. Okay, we consider this. Besides, we have the same procedure for another state. So if we want to have a meaningful comparison, you have to consider all of them, maybe separately or combine them, for example, by two norm or infinity norm. I think in this way, we can look to all variables and all set of real data. But as I told earlier, this makes our comparison and analysis much more complicated. And we have to see if it works well at the end. We have to do careful consideration in this regard.
When I asked him a similar question, I said, what the effect of the people have a theory about that? That's why we want to consider that. What do you think?
No idea for now. Yes.
Who was that professor? Uruguay. Maybe we know the name if you tell us the name. Okay. Because we know many people in that area.
Oh.
King Abdulaziz. Coast. Okay. Okay.
Thank you for your
Thanks
consideration and question.
for our Professor Jajarmi for the very good talk and also for the audiences. Let's give the certificate.
We would like to thank our Professor Amin, Professor Dr. Amin Jajarmi for an enlightening presentation, and Professor Dr. Özlem for sharing this session. Professor Dr. Özlem has presented a few of appreciation to our distinguished speaker, Professor Dr. Amin Jajarmi. Dear participants, we will now continue with the parallel sessions. There will be several simultaneous sessions. 4 sessions will take place physically in the time of 3 sessions will be held online. You are kindly invited to join the sessions of your choice according to your intent. Please follow the program schedule for the whole operations and online access detail. We wish you all great pleasure.
Seçeneğin 4. burada.
Efendim?
Onlar seçeneğin 4. burada olacak değil mi?
Aynen burası. Çevirsiz misiniz hocam? Tamamdır.